Let me continue with now, we are talking a lot about basic concepts. The first thing that we talk about is idealization, free body idealizations, thing where you get analysis model. Just now, we were discussing about connection and support. For class, it is important to know what forces will occur at the connections or within member sections. Okay, so because this is important, I will emphasize again that during structural analysis, because if you miss any of the forces, if you omit any of the forces, then the rest of the calculations will be wrong. Okay, so get this correct. So again, the questions that is important for you to ask is, what internal forces will happen here? Internal forces mean forces which happen in the member connected here. And what internal forces will occur here? Internal forces here, if you cut across this member, so what internal forces will occur here? Okay. So these are the questions that we need to ask when we are doing structural analysis. If there is a connections, what forces will happen there? Internal forces. If it is support, what kind of reaction forces will happen there? Now, we look at hinge connection first. So if there's a hinge connection, just now we look at the hinge support. If there's a hinge connections, this member connected to this member at the hinge. So we will have two internal forces happening in the member itself, So how to show that thing? You have to cut across here. This symbol we use to represent cut. We might also be using this symbol to represent cut later on. So you need to cut, class, you need to cut across a member, then only internal force appear. So when you do the cutting, if it's a pin connections here, so in this member here, you get two forces. And because this member is connected actually to this connection, so at the connections here, you also get two forces here. The red one, same thing here. And the red one and this red one and the black one, they are pointing in different directions. And same magnitude. Here they are pointing in different direction, same magnitude. Okay, so that is what will happen at the pin connections. There are two internal forces. If it is a rigid, the same thing. If it is a rigid, what will happen? How many forces? So again, we have to cut. So if you cut here, then in this member here, in this member here, at this, in this member here, which is connected to these connections, you have three internal forces. Now, internal forces, this force, and moment. So again, this and this different direction, this and this different direction, this and this different direction. This moment here also it is rotating in different direction. The rotation is different, but their magnitude, they are the same. The same thing here, this and this opposite direction, this and this opposite direction, and this, they are acting, they are rotating in different directions. If this is counterclockwise, this should be clockwise. If this is clockwise, this should be counterclockwise. They are always acting in different direction, but with the same magnitude, because this and this actually, they are together, the same section. This and this, they are same section. Only thing, we cut it off, we separate them into two. So the important thing at the pin connections, there are two internal forces in the member connected to that joint. With a fixed connection, there are three. Okay, there are three. And the directions here, I show you, we can also show it in this way. The forces, you can show in this way. Also, if you don't like these directions, if it is more convenient to put direction like this, we can also show in this way. But it doesn't matter you show in these directions or you show in this direction, there are only three independent ones. There are only three independent ones. Only that we show them in different different components. Yeah? Different components following different axis directions. Either this one or this one. Okay. When should we use this and when should we use that? I think when we go to analysis, then I will emphasize that, explain about that again. So now we will have to look at the basic, one of the basic equation that you need in the analysis is equilibrium equations. Equilibrium equations. So you draw, this is analysis model representing the problem, actual problem that we get through idealizations. Then we draw free body diagram. So free body diagram, we must decide which part of the structures we want to draw the free body diagram. Which part of the structures. In this case, we draw for the whole beam. We draw for the whole beam. Okay, so this is a free body diagram. So remember, reflected correctly, the support, how many reactions here and how many forces here. Pin and fix. So after you draw this free body diagram correctly, showing all the forces, the unknown one, the red color, and the known one, this magnitude is given, for example, 50 kilonewton. These are the unknown one we do not know yet, that we need to do calculations. But this must be drawn correctly, the free body diagram. Then we use equilibrium equations to get the red one, unknown forces. Okay. So free body diagram, this one we have emphasized many times. By now you should get it correct. It represents the structures. So it can also represent part of the structures. So it depends on what part of the structures you want to draw the free body diagram. And you don't see any support. You remove all the supports or any other members connected to it. You remove everything. You take it separately, one diagram, but you have to represent the effect of other parts, effect of support, effect of other members in terms of forces. That's why you see only forces here. So free body diagram is a diagram representing the structures where all supports and surroundings have been removed and you replace with only forces, which include moments that act on the structures. Then, once you get this correct, then you apply the three equilibrium equations. Three equilibrium equation for planar problem. For planar problems, equilibrium equation for planar problems. So for planar problems, we have, for each of the free body diagram that you draw like this, you have three equilibrium equation, three, which is the one that you already learned. So the first one is, if you take this as x directions, then summation of forces in x direction should be 0. If this is a y direction, summation of forces in y direction should be 0. And the third one is, these are related to forces, and the third one is moment. If you take moment caused by the forces at any point within this plane, and within this plane, it can be here, it can be here, it can be anywhere. Within this plane here, then the moment should be 0. Okay, summation of moment around z-axis, x, y, and another axis is z. So the moment acting in this plane caused by the forces within this plane around z-axis. So z-axis is the third axis here. It should be 0. So these are the three equilibrium equations that we have. That we can use this, write down the equations, then you can solve for all the unknown forces in this problem here. So these are the meaning. Summation of forces in x direction 0, algebraic sums. If you put all the forces together on one side and the other side you make it equal to 0, so you need to consider the sign, positive, negative, depending on which direction you consider as positive. The same for this one. And moment. So moment, if you put all the moment caused by the forces, including the moment caused by this moment, on one side of the equation, so you need to consider whether that moment is clockwise or anti-clockwise. Then you choose whether you want to use moment clockwise at the point that you want to take moment as positive or negative. So you have to consider the positive negative sign if you put the moment, everything on one side, and the other side is equal to 0. So that is an algebraic sum. Algebraic sum, meaning that you need to take into consideration the positive negative sign of the moment. Okay, so a simple example of calculations of reaction force using equilibrium equations. This is a free body diagram. This is a free body diagram of a simply supported beam. You have reaction force here, reaction force here. And there's a load acting here, 10 kilonewton. So this one, if you, this is a free body diagram. So these are the loads. These are the loads. Magnitude is known. These are reactions. Magnitude is not known yet. So we draw this free body diagram showing only all the forces known and unknown. Then we use equilibrium equations. Depending on which one you want to use, which force you want to calculate, then you have three. You can choose any one of the three in any sequence, but you have only three, and to solve for all the unknown forces. In this case, the reaction force. So if I take moment at A, this is A here, then I get this 6. This is just to refresh you. 6 multiplied with By, you get this moment. I consider this as positive. Yeah, 6 multiplied with By, so take moment at A, so this is this direction of the moment. And then the next one is this, multiplied with 2, 2 multiplied with 10, and this you get moment like this. So this one we consider as counterclockwise, consider as positive, then clockwise consider as negative. If you don't like this, you can also consider this as negative, but then this one must be positive. The answer will be the same. So whether you want to consider this side clockwise as negative or anti-clockwise as negative is up to you, but you must consider the sign consistently, correctly. Here I consider clockwise, anti-clockwise positive, so the clockwise become negative. So you get the answer, By is equal to 10 over 3. And you get positive means the direction that you assume is correct. So this is just a simple refresh of what analysis is all about. What analysis is all about. And you apply equilibrium equations. This is moment equilibrium equations. So each one of these must be moment. Each one of these must be moment. So do not mix moment and then mix with forces here, so that is no meaning in that equations. So moment equilibrium equation, make sure all the terms appearing here, there are moment. So moment must be force multiplied with perpendicular distance to the point where you want to take the moment. So do not make mistake in that basic concept. Okay? So if you want to find what is AY as well, so once you calculate BY, so you use another equilibrium equations. So you get BY plus AY, and that is coming down minus W equal to 0. So you substitute BY that you have calculated into this equation, then you get AY is equal to this. So you have, again, this is positive value, then direction that you assume is correct. If you get negative, means direction that you assume is wrong. Okay. So this is what analysis is all about. Okay, the important steps. Look at the problem that given to you. Draw the free body diagrams correctly, and then apply equilibrium equations, the 3 equilibrium equations, to solve for all the forces that is unknown yet and you need to solve. So free body diagram class, free body diagram is a very, very important diagram, and it must be drawn correctly. It must be drawn correctly. So to draw free body diagram correctly, then you need to get all the basic concepts correct. What are the supports and how many reaction force that you should consider? Okay, so those are the important message that I want to emphasize again to you, free body diagram, get it correct. So now I would like to end with this because you have to move to other class. So free body diagram, it can be drawn for, it depends on what parts you want to draw. Okay, what parts you want to draw. It can be the whole structures, it can be part of the structure, it can be connections. Okay, it's up to you, it's free to us. We can cut the structures into many pieces and then we can draw the free body diagram for that particular piece, or we can consider the whole structures. So I end here with 3 examples here. Example 1, example 2. This is a beam, this is a pin support, this is a roller support, this is a frame. You have an inclined member fixed here, pin support to another member. This is a pin connected to another member, and you have a pin. Then you have a pin connects a pin support here, and finally this is a frame example, pin support, fixed support, roller support, and all members, these members rigidly connected to this member, rigidly connected to this member, this member rigidly connected to this member, and this member rigidly connected to this member. Okay. So we can draw a free body diagram for the whole structures. So it becomes 2 reaction forces, 1 reaction forces. This is for the whole beam. So it's good to indicate X and Y here, which one is X, which one is Y. So we put AY here, AX here, BY here. The next one, if we want to draw free body diagram separately, so we separate this at the joint here. So these are the free body diagram for part AB. This is the free body diagram for part BC. And what is important here at the joint here, this and this must be opposite direction because this is pin connection, only 2 internal forces here. B and B magnitude the same, opposite directions. So forces common to 2 members. Now this member connected at B. Shown acting in opposite direction but with the same magnitude, Fixed support, 3 reaction, pin support, there are 2. So this one, I leave it here with you to go through this. This one, we separate this into 3 parts here. This part, if we cut here, we get this. And we cut here, then we get this. So we cut here, so we separate this frame into 3 parts. And because this is frame, so the internal forces here, when you cut them, internal forces, there are 3. Reaction forces, depending on the type of reaction there. How many you have, and how many you have here. Okay. So in general, forces acting on the sections. Yeah, here when you cut through then you see the forces appear. So in general, forces acting on the sections in the plane structures, there are 3. So you have axial force, shear force, bending moment. There are 3. In general, for any members in the 2D structure or planar structures. Okay. So last, I will stop here, okay, because you have to move to other class. So we will do this. We will continue. I think